Hi, Liz.
Hi, Michelle.
How you doing?
I'm doing well, thank you. And you look well.
You as well. So today we're introducing podcast number 2. It is Aging as an Adaptation, which
Yep.
is Dr. Green's theory based on all of his research and a very important computer modeled study by Andre Martin that
Yes.
illustrates how aging is adaptive. And the reason this is important is that classical evolutionary theorists say that aging is not adaptive.
Right.
However, they can't explain it. It's not based on any scientific method. So it's one of these
Yeah.
things since Darwin, they've just gone with. You know what it kind of reminds me of is what's happening in archaeology right now, where they're finding all these advanced civilizations that are 12,000 plus years old. And it's making all these scientists kind of misfire because they don't want to. I don't know why you can't admit you're wrong. You know what you know with the evidence that you have at the time that you have it. And when you find new evidence, it's new evidence. It doesn't mean you were wrong or stupid.
Yeah.
That's what this reminds me of, because now we're gathering data and we're doing studies, and this particular study really, as a computer model, proves how aging is adaptive, because you describe it better than I do, Liz. Why don't you describe the computer model?
Well, it's just a model that basically puts agers against immortals, and they all start out with the same number. They have equal number of spaces on a grid, and they have fitness levels. And over time, the fitness levels of the agers grow because of the genetic gene pool changing quicker than it does for the agers. So, for the non-agers. So basically, over time, the immortals go extinct. So there's an advantage to shorter-lived animals, and that's what the computer model shows.
Right.
But I also want to say what you said about the archaeologists is it's the same thing with the amyloid beta theory of why we have Alzheimer's, or why people get Alzheimer's, and it's totally wrong. I mean, they have 30 years of trying to cure it or halt it based on the amyloid theory, and they aren't getting anywhere. So
yeah. So Alzheimer's disease is our next podcast, number 3.
Right.
So we'll get into that too. But yeah, the computer model is interesting, especially they focus, there's several models that we focus on the first one that shows how non-agers can overtake agers. No, the other way around. Because they throw in external variables. It's more representative of the real world. We have a changing environment constantly. So we are able to adapt to those changes and become more fit over time, and therefore it's adaptive, and I can't explain it as well as you and Dr. Green can, but this is what he's going to do right now. Okay, debunking classical evolutionary theory, which is pretty bold, but seems like that's happening everywhere now. So we're going to let unless you have anything else to say, Liz, we'll let him take it away.
I think that's great.
All right.
Thanks, Michelle.
All right. See you later.
Okay. Bye.
Bye.
The question of whether aging is adaptive has been the number one question in the field of aging ever since Darwin's classic paper, Origin of Species. So Origin of Species presented the idea of natural selection. This is a revolutionary idea, the idea that animals were evolving without the hand of God, just by natural selection. A totally revolutionary idea for the mid-19th century. Then Darwin presented the idea that traits were adaptive, were selected by evolution because they were beneficial. And that was the whole basis. That was the whole basis of natural selection, that a trait was beneficial. Darwin focused on beneficial to the individual. This worked fine when people were explaining the evolution of things like nails and claws, but it ran into a problem when it came to aging. It was obvious that aging is extremely prejudicial to the individual. Aging causes the death of the individual. If an individual dies, they can't have offspring. The classic sort of like concept of fitness was able to have offspring. If something caused you to die, you couldn't have offspring, it seems self-evident that that was not beneficial. So that basically, everyone had the idea that aging is not beneficial. Darwin had a different idea. Darwin was much, much smarter than everybody else. Darwin said, if an animal is like doing something that puts it at a disadvantage, it'll be driven to extinction by the other animals that don't have that trait. Now we have lots of short-lived animals and long-lived animals. If being short-lived didn't have some sort of benefit, the short-lived animals would be driven to extinction by the long-lived animals. Therefore, there must be some benefit to having a short lifespan. But Darwin said he could not explain what the benefit was. He had no idea at that time, at that place, he had no idea what the benefit was. But Darwin, being an extraordinary genius, knew enough to say, there must be a benefit. I just don't want to know what it is. But according to my theory, if there wasn't a benefit, we wouldn't have short-lived animals. But everybody else didn't like that explanation. And they decided that, no. The way they looked at it is that they decided to look at this without having any evidence, without using science. They decided to fall back to how Aristotle would have looked at it as in ancient Greece, using classic deductive reasoning, using the syllogism to try to figure it out. And the syllogisms go premise, premise, conclusion. So the first premise was, for a trait to be adaptive, for a trait to be selected by evolution, it must be adaptive. It must be beneficial. If it's not beneficial, evolution won't select that trait. Then they said, premise number two, aging is not adaptive because it causes the death of the animal. That's harmful to the animal. It can't have more offspring, just clearly harmful. Conclusion, aging will never select genes to promote aging. Aging will never select pro-death genes. And they sort of like called that theory, they consecrated that theory with the term evolutionary theory.
Dr. Green?
Yes.
Sorry, I don't know if we're allowed to ask questions in the middle, but could you tell us the approximate timeframes of these? Like, I know Darwin was around 1860s.
Darwin's paper is 1859.
1859. And what about this theory of evolution?
Darwin doesn't have a specific theory of his theory of evolution.
No, I know, but you just said there was another theory of evolution.
He doesn't have a specific theory. He has, what he does, he presents this paper of natural selection. That's right. Contribution, natural selection. The animals are sort of like choosing traits through natural selection. That's Darwin's whole contribution in 1859. Certainly the people coming after Darwin, they're asking Darwin about it, and Darwin's saying, he has no explanation of a benefit of a short lifespan, but he thinks it must have a benefit, or those animals would be driven to extinction. The rest of people just come up with the idea that what they explained, that the idea that evolution would never select genes that promote death. Evolution would never select death genes, and then they consecrated that theory by calling it evolutionary theory.
Okay, that's what I meant. That's when I asked you, when did this evolutionary theory, what time frame was this?
Evolutionary theory starts from the very beginning. I mean,
Okay.
basically from the very beginning, this is developing. It's simply going from a theory to dogma to accepted as absolute fact, to sort of like everybody in the field accepting the idea of evolutionary theory becoming the basis. And so now at this point, evolutionary theory becomes the basis of everything in the field of classical aging. All the papers start off with evolutionary theory rolls out genes to promote aging. That's just sort of like the basic idea. And everything everything springs from this. So they finally get into sort of like recent book, it's sort of like Handbook of Aging, 2019. What they sort of like eventually come to is, there's no genes involved in aging. And because there's no genes involved in aging in living things must be the same as aging in inanimate objects and materials. So that basically there's no difference between a time related decay, instead of, say, an inanimate object as a living thing, because there's no operation of genes. Basically, they say the model of aging is a car. A car is built to last a certain amount of time, and then it falls apart. And then they sort of like explained it with a car doesn't, they thought that was a very, very clever explanation. A car doesn't need any blueprints to tell it how to fall apart. And because a car doesn't need any blueprints to tell it how to fall apart, living things like people, they don't need any genetic instructions to tell them how to fall apart. That just happens. They're just built to last a certain amount of time, and then they simply fall apart and age and die. And that's the idea that aging was not an active process, intentional process going on. And then they actually came to the idea that aging was basically negligence. They said, they actually sort of like decided that they knew better how evolution should work. And they decided that God had made a big mistake. Evolution had made a big mistake. They should have eliminated aging. And evolution was just negligent and failing to figure out a way to eliminate aging, because aging was just harmful to animals, and it just should have been eliminated.
Because there's no benefit.
Yeah, there's no benefit. It should have been eliminated. So he basically looked with like an unbelievable degree of chutzpah. They looked at the natural world and they said, this is wrong. It should work this way. We have a better idea of how the natural world should work, and it shouldn't have any aging in it. And maybe they also thought it shouldn't have bugs either. I don't know, but I don't know about the bugs part. But they definitely sort of like were figuring out that they had a better idea of how the natural world should operate. The only problem was this was not based on anything called science. It was based on the way Aristotle would have looked at it in the ancient Greece. Ever since 1640, Francis Bacon came up with the scientific method. The scientific method was based on observation and experimentation, and then observing what's happening in the real world, and then sort of like developing sort of like ideas based on your observations, and see if that's sort of like checking with what's going on. It's like that kind of a feedback of sort of like about everything based on scientific observation and experimentation.
Right. Dr. Green?
Yeah.
Wait a minute, what was my question? But the reason they felt this way is because they had no explanation at all as to what was really or potentially happening. So they decided that we'll just default to humans wear out just like inanimate objects.
Right. That's exactly it. It was basically, the point is,
It was a conundrum. They couldn't figure it out. So they were just
basically, this to them, this was common sense. The problem is, science isn't common sense. That's how the problem is, it's sort of like the field of science, basing things on a premise is extraordinarily risky, because it's very likely that your premise is going to be wrong. In other words, that's sort of like science isn't based on coming up with premises and deductive reasoning. Science is based on observation and deductive reasoning from that. So that was the whole problem. The whole problem is everything was based on the premise that aging was not adaptive. If aging turns out to be adaptive, the entire field implodes. It's like, it means everything they have been saying for the last 150 years is wrong.
Dr. Dreen, is now a good time for me to share your chart, or you're going to tell me when?
You can show the chart of just sort of like what science is. That's sort of like chart. It's just like this, just to make the point of what science is.
Okay, hold on. Let me get to that one.
The next chart, science. This is the idea about science. Science is based on studying the world through observation and experimentation and testing the theories that you have against the evidence obtained. So that's what science has been since 1640. What science has not been is about using common sense and deductive reasoning. That was the idea of how things worked in the ancient Greek method. That was Aristotle's method. And modern science was a revolt against Aristotle's method. And basically, this war was settled in 1640 for almost every form of science, aside from the field of aging. Almost every other field of science is totally based on the scientific method and observation and experimentation. Aging became the only sort of like field that was not acting like a science, because it was not based on observations. Now, but the question is, why is this important? Why it's important is that, well, it's important for first, if it's important to understand what's going on with aging. Everybody sort of basically dies of aging. All the sort of like, if people get older, they have all the age-related diseases and so forth, and everything that's happening is related to aging. Understanding what's going on with aging is of the highest possible importance of anything, especially for like science in general, that we understanding it, but medicine in particular. Medicine in particular has to understand what's going on with aging. The entire field right now of anti-aging medicine is based on the idea that there's pro-death pathways. Pro-death pathways require metabolic pathways. Metabolic pathways provide druggable targets. In other words, they provide targets of drugs and other things to reduce the things that's driving aging. So the idea, to give an example of one particular thing, you have the idea that mTOR driving aging. If mTOR is driving aging, you can block mTOR with rapamycin. So like mTOR stands for target of rapamycin. Rapamycin blocks mTOR. By blocking mTOR, it slows down aging. So understanding, but classical aging basically said anti-aging was not possible. It was basically not possible because there were no pro-death pathways. Pro-death pathways was impossible because of what they called of their idea of how evolution worked. And therefore, anti-aging was basically impossible. That's the whole idea. Anti-aging, certainly the current field of aging, is totally opposite and antagonistic to the idea of anti-aging medicine. This sort of like it limits the expenditure of the field of medicine being involved in anti-aging, the field of sort of like other sort of like research being involved in it. The field of sort of like, in other words, the whole body of science and medicine is not involved in anti-aging because of the theory that there's no pro-death pathways. If people accepted the idea that evolutionary theory was completely wrong, that the idea that the evolutionary theory that you could not have the evolution of pro-death pathways was completely wrong, then they would be, then they could accept the idea of anti-aging medicine, of trying to sort of like look for pro-aging pathways that you could block with drugs and therefore slow down aging and age-related diseases. So it becomes a question of whether a few thousand people are being treated or 100 million people are being treated. If it's a generally sort of like held idea in the world of science and medicine that yes, there are pro-death pathways that promote aging, and we should try to block those pro-death pathways to slow down aging, then you'd have millions of people involved. Like, it'd be the number one thing taught in med school, that there was this. There'd be sort of like a basic part of medicine. It'd be a basic part of sort of like, everybody involved in like primary care medicine. The basic idea would be we should be blocking pro-death pathways to slow down aging. And this would then be sort of like something involving millions and millions of people.
Mm-hmm. One other thing, Dr. Green, I have a question about when you say evolutionary theory, I always, I guess I always thought that Darwin was associated with the theory of evolution. So when you say like the whole thing topples, we're really only talking about the classical aging theory portion that says aging isn't adaptive, because Darwin's portion was fine, apparently. He said he didn't know. He didn't understand.
Right. Darwin's basic theory is natural selection.
Right.
That's like,
okay.
Now, when it comes to sort of like evolution, it's like the Constitution. People can say the Constitution means this. People can say the Constitution means that. And like the Supreme Court Justice, it doesn't matter what you say. But the idea is that people can say it's like there's the Constitution and what people say it means. It's sort of like, in other words, that changes every administration. Now you have the same thing with like evolutionary theory. You have evolution, but everybody can have their own idea about how it works. and call their idea of how it works evolutionary theory. I mean, in other words, I believe in evolution 100%. Everything I'm talking about is based on evolution. I just think evolution works 100% different than how they see it works. I see them having taken evolution and turned it on its head and presenting a totally wrong idea of what's going on.
Right.
So when they call it evolutionary theory, yeah, they could call it, that's their theory. It's certainly not my theory.
Yeah, we're presenting Dr. Green's theory, and we're going to back that up with some evidence.
Right, that's the idea. This basically is about what happens when scientific evidence meets evolutionary theory as presented by classical aging. The idea that so the question is, and this comes down to the question of, is aging adaptive? So the whole thing comes down to this single question: is aging adaptive? It turns out, though, that this was actually a very difficult question, because even Mikhail Blagoscaloni, who was like the smartest person or the smartest people in the last 100 years in the field of aging, he accepted what was called evolutionary theory, and that you could not have programs that were selected to cause death. And that's why when he came up with his theory of mTOR, he had to develop his own word to explain it. Instead of saying there was a theory, instead of saying mTOR was a program, he had to say it was a quasi-program. A quasi-program was a word that he made up to explain how mTOR could be working and not sort of like violate the idea of evolutionary theory. If he has not sort of like believed that evolutionary theory as presented was correct, and he thought that sort of like aging was adaptive, then he could have just said mTOR theory. In other words, he said, this is a real theory. mTOR is there to promote aging and death. But the problem, he had no explanation of why that was good.
But didn't so he calls it a quasi-program, kind of, from what I've read, it seems like he's thinking along the lines of there was a mistake, because the mTOR is kept at the same rate. So it's good if people are speeding along in a car, or when they're growing. When people are growing and mTOR needs to be high so that they can grow, in the end, it was hyperactive essentially, and that was a mistake.
But,
did he say that? Something along those lines?
Basically, he's having two ideas. His idea is mTOR is driving aging.
Right.
That's his basic idea. And I agree with him 100%. mTOR is driving aging. I just think mTOR is a real program. It's there for the intentional purpose of causing death.
Okay.
He says, no, that's not possible. It must be just a thing that was left over by accident. It's an accidental program. So he says this whole aging concept from mTOR is just one big accident. And then he gives an analogy to explain it. His analogy is, suppose somebody has a program to boil water to make some tea, and they put a pot on the stove. And they sort of like, that's to boil the tea. Then they leave the stove on, and the stove then sort of like, the pot and water boils away, and the pot breaks. And then he says, the program was not a program to break the pot. It was a program just to make the tea. It just kept on running. It's just after we made the tea, it just kept on running and destroyed the pot. He's basically saying aging is like a demented old person not turning off the stove.
Right. Well, and people used to not live for very long. So problems with mTOR probably never came into play as much as they do now that we have longer lifespans.
mTOR is always a major role in animals' death. So like in the wild, different animals were dying of different things, but for the most part, animals were dying as a result of mTOR. You could sort of like look at sort of like what happens with animals if you're young and fit, and there's sort of like a wolf chasing after you, you can get away from the wolf. If you're sort of like older and a wolf is chasing after you, you're a little slower and the wolf catches you.
Okay.
Now, are you dying of aging or you're dying of the wolf attacking you? Well, the idea is that aging sort of like kills you that way. It causes you to lose a little one step. You can't, if you're an animal that has to escape prey, you can't get away. If you're an animal that has to catch your prey, you can't catch it. So you're not dying of symptoms to like aging the way humans are dying of aging. You're dying of aging because aging has caused you to become impaired, and now you can't survive. Now you can't meet the challenges of survival because of sort of like the changes that aging has taken place in you.
Okay, I understand.
So, right, it's that idea. You figure if a bear was chasing the three of us, I would be the bear one that got caught by the bear.
And Michelle would get away. I'd be the second one.
It would be the one getting away. And you can say, oh, but so like, did I die of aging or I die from the bear? But the point is, if I was 25 years old, I probably could have gotten away. Maybe if I was like lucky, like a better chance. At least if I was 5 years old, maybe the bear would have caught Michelle instead of catching me.
How old were you when you ran the it was the New York Marathon, right?
I was around 40.
You're around 40.
So the point is, in the wild, animals don't get to this sort of like stage of complete decrepitude and failure that humans get to in sort of like civilization. All they needed to do is much more analogous to a professional athlete. In other words, a professional athlete could still be a very good top tennis player, but if like 40 years old, they're not winning any more Grand Slam titles. Well, they still could be, in other words, it's slowed them down. It's killed their professional career as an athlete by slowing them down. And generally, it's killed the professional career as, say, a grandmaster chess player by slowing down their thinking. So it's like that. Aging sort of like is causing impairments. It generally doesn't have to go to sort of like the bitter end. It only goes to the bitter end in like humans, because no matter how bad off they are, medicine and like society can keep them alive. So the question is, the critical thing is aging adaptive? So that's the sort of like, that's the key thing. That's the most important question in medicine. And to understand that, you need a computer program, because aging is involving millions of variables. To sort of like, to give you an example, evolution of like complexity, evolutionary theory, you could think of having a complexity on the level of 1. They think of an animal in a situation where the will doesn't change, there's no will, the will doesn't change, and you don't have the action of any genes, And a situation where you don't have the action of any genes and the world doesn't change, animals that don't age always sort of like wipe out ages very, very quickly. The ages have no benefit. They immediately get out. The ages totally get wiped out by the animals that don't age in a world that doesn't change. The question was, what happens when the world changes? And of course, we live in a world that changes dramatically all the time. From little changes, like what we see, so forth, to enormous changes, like an impact that wiped out the dinosaurs 66 million years ago, totally changing what was going on. And so, throughout evolution, there's been 5 mass deaths. It's vary by different things, showing the extraordinary effect of the changing world. So you have all this change. You also have the effect of genes. In sort of like a billion years, we've gone from a one-celled animal to very complex animals. That's the effect of genes. Genes are sort of like causing animals to see genes are continuously changing, and animals are continuously changing. So the idea of classic sort of like aging theory did not consider the effect of genes, did not consider the effect of a changing world. It had a complexity of what I would say is one. Just the program that we're going to look at, I would say, has the complexity of 1 million compared to like how classical aging looked at it. If you looked at the real world, you could probably say that has a complexity of 1,000 times greater, 1 billion. However, this sort of like program, which includes factors like a changing world and different lifespans and genes causing animals to be able to evolve, that sort of like adapts, that sort of captures a great deal of what's happening in the real world.
Dr. Green, is this a good time to, I can present the...
Let's start with sort of like the slides. Let's go to the videotape. They say, let's go to the videotape.
Okay, so let's go to the what? To the videotape?
Yeah, that was just an expression. It's sort of like, look, so we're going to
Let's look at the slides. Okay, so Dr. Green is going to present information from a published paper written by Andre C.R. Martins. He's with the University of Sao Paulo, Brazil. And I guess he's also involved with the École Polytechnique in France. And we want to thank him for his excellent genius work called Change and Aging Senescence as an Adaptation. Keyword. Okay, so you want me to go to the first chart?
Yeah, the first chart. Okay, so what Martins did is he sort of developed a computer program which you could think of as a scientific study to see what happens with aging and what happens when you have different sort of like, you introduce change into the world. So the name of the paper is Change in Aging, Change in Aging Senescence as an Adaptation. So he's basically saying change in aging and senescence is an adaptation to the changing world. And now, in order to study this, he develops a computer program, and it's based on a grid. So the grid might be 100 times 100 little squares. And then he has 2 different sets of animals. The 2 animals are identical, only one is immortal or one doesn't age, and the other is aging, and they'll all die after a couple of generations. And he can set that number of generations from like 1 to 2 to anything up to sort of like 10. He can have any number of generations. At that point, all the animals at that age will automatically all die. And then,
Dr. Green, hold on. So what you're saying is that whether you're an ager or a non-ager, you still die within like 10 generations, within 10 generations, because you can die of other things besides aging. You could get in a car accident, or you could have a bear eat you, or you could.
non-agers are immortal, theoretically immortal.
They're theoretically immortal, but they still die for various reasons that are not due to aging.
Right, they die due to combat.
They die due to combat, or a bear eating them, or something like that.
In the program, they only die from one thing. They die from combat.
Okay.
So now the ages have a certain fixed lifespan based on how long it takes to reproduce. So that's how the lifespans are counted. So it might be one lifespan or two. Whenever you reach that lifespan, like if you're set to have like two generations, as soon as you reach 2 generations, 100% of those animals immediately die. Now,
So agers are dying of both, non-agers are dying of both combat and of aging.
right. So now they're all going around in a grid. And a grid is, if you think of like maybe 100 times 100, sort of like, squares, 100,000 sort of like boxes. A box can only support one animal. If 2 animals land in the same box, one of them will die. And which one dies is based on fitness and luck. So they have a way to calculate the changing fitness of the animal. And then they have a little kind of calculation that depending on your fitness, it gives you a little better chance of survival. It's basically they're taking the average of the 2 animals' fitness and then you're dividing and so forth. And it turns out that if you're a little bit more fit, you have a little bit better chance of surviving if you both sort of like wind up in the same box. Whether you survive or not is still a matter of like luck. It's just depending on the calculation is depending on your fitness, you'll have a better chance of sort of like the animal with a higher level of fitness will have a better chance of defeating an animal with a lower level of fitness. Now,
because you can adapt to the changing environment, right?
It's like the fitness has changed. We'll go over the reason why the fitness has changed. But the problem thing is, when they land in the same box, their fitness score determines the chance of survival. They all start off with the same fitness score. And then they inherit the fitness score with each generation from their parents. So if their parents were like, whatever the fitness score the parent had, that's what they inherit. And then they keep on going on. And this goes on, but the point is, this goes on for 10,000 generations. Over 10,000 generations and 100,000, like 10,000 individuals, very little numbers turn out to make a huge difference. They wouldn't make a big difference if it was just a couple of generations. But the idea is that they're running the program for many thousands of generations. Now, the other things they sort of like put into the program is they make up a sort of like a thing for a changing world. That's one sort of like variable. And another variable they make up is what they call dispersion. How far the animal will be born from its parents. So that's sort of like That's sort of like basically how far an animal will sort of like move from where it's born. Like little rabbits living in the same rabbit hole, that's slow dispersion. Animals swimming in the ocean, that's high dispersion. So it's like that's just sort of like how much dispersion they have. And in this case, is how many squares that are born away from the parents. So there's that. And then they throw in mutations. Mutations are at random. They don't occur all the time. They occur very infrequently. And they could be good or they could be bad. And they are randomly good or randomly bad, and they increase the fitness. So if you inherit a good gene, a good mutation, you increase your fitness. If you inherit a bad gene for mutations, for like fitness, you would decrease your fitness. But generally, if you develop a decreased sort of like degree of fitness, you'll never get to the stage of having offspring. So you just sort of like pretty much die. It's only the sort of like, but you might still survive. But sort of like you might survive or not survive depending on your level of like fitness. So animals are developing a change in their fitness due to sort of like the change in the world. Due to the change in the world, they're like becoming less fit each generation. So each generation, they're automatically becoming less fit because they figure you're like less adapted to the world. It's like because the world is changing. So since the world is changing, you're less adapted to the world with each generation. And then
aren't the non-agers, because I'm presuming the immortal non-agers, they can keep reproducing.
Yeah, everybody reproduces at every sort of like generation. The agers and the non-agers, at every sort of like it's like this time is measured in generations, and in every generation, each group reproduces. Each group has sort of like one offspring after each generation passes.
Okay, but the agers die after a couple of generations or so, and the non-agers don't. So the non-agers are passing down their old gene pool.
Yeah, the agers will sort of like die after like 2 or 3 generations, depending upon what it's set for. They'll have different things setting with different lifespans. That'll be a reason why they die. And they could also die because they wind up in the same box and they sort of like die of combat. So you can, and what's changing continuously is fitness. That's the critical thing. Now, if you look at these,
so Dr. Green, so the agers are getting fitter and fitter and able to overtake the non-agers in this model is what is happening.
And sometimes that they do, sometimes they don't. That's where we have to look. It's sort of like what happens is sort of like depends on the different variables. And they start off with one sort of like model run. So this is a model run, and it's taking place over time. And the time is going from left to right, and then from down, and then from left to right. So,
but if you kept going, Dr. Green, wouldn't it eventually be all blue because we have no such thing as non-agers?
Well, depends on who wins. So, but the point is, in this sort of like plan, this is the beginning, and this is the end. And then they show the first box. And the first box, you can see every little sort of like this. These are all little squares. It's hard to see, but they're all little squares. And you have red squares and blue squares. And animals that have a low level of fitness have a pale color. And the darker the level, the darker the color, the darker the color, the greater the level of fitness. So the color is indicating the fitness in the sort of like diagram. So you can see
the tone, the deepness of the color is the thing. So it says
more in that.
Both for blue and red, lighter tones indicate a smaller fitness, while darker tones correspond to a higher fitness. green spots correspond to places where no living agent is present.
And the diagram, the group of red, that's all not ages. And
Right.
it's all ages. And this is how they start off. They start off with a completely equal number. And then it's sort of like changing. It's sort of like initially, and the fitness is changing. So this is like the third one. But the third one, you can see there's much more red than blue. The red is sort of like, been sort of like, because the blue ones, the ages are dying. Now you have this one, there's still more red than blue. At this point, things are starting to change. Now you can see that the blue, they're basically a little more red than blue, but the blue is starting to get real dark. So the blue is becoming more fit than the red. At this point, once the blue becomes more fit, then their numbers can start sort of like changing. Here, just sort of like the blue now, they're much darker and they outnumber the red. Here, the red has disappeared. Here, at this point, the red is sort of like very, very small. It's totally dominated by the blue. The blue is sort of like the ages in this run is wiping out the non-ages. But it's sort of like they start off with the same numbers, the same little fitness, and over sort of like a long number of time, the ages develop more fitness, and the higher level of fitness enable them to win. So
Which makes sense.
they're sort of like the ages were able to win in this run. Here's a sort of like example of this run, of something like this. You can see this took this took 8,000 generations for a resolution. And it starts with them each having the same number. Right away, the ages number drop, and the non-ages sort of like increase because they have, but then after a period of time, the ages start sort of like increasing the numbers. So this is the numbers. So here the ages numbers are increasing, and now the non-ages numbers are decreasing. And at this point, the non-ages, the immortal group is being driven by extinction. They've sort of like been wiped out. And this chart shows the change in fitness. So you can see what happened is the non-ages, their fitness stayed about the same. They're giving them a fitness score from 0 to 1.2. But the non-ages fitness is increasing. It's increasing from an initial start-off score of 1. It's getting better. It's getting up to 1.1. So things are sort of like not improving. That little change in sort of like fitness is enough over 8,000 generations for the ages to wipe out the non-ages. But notice this took 8,000 generations. Okay, let's look at the next slides. Okay, here's a sort of like thing in which the non-ages won. Just sort of like, I mean, in other words, the non-ages, this is the non-ages, this is the ages. You see, this is blue, red. In this one, it only went for 1,400 generations. The other was 8,000 generations. But in this one, the ages sort of like numbers drop, and then they're never able to recover, and then they just get wiped out. This is the fitness of the sort of ages and non-ages. The ages is developing slightly sort of like more fitness, but it's definitely not enough fitness to overcome the sort of like the death of sort of due to aging. And this one, they get wiped out, but they didn't survive long enough. So they got wiped out in 1,000 generations, 1,400 generations. And generally that's the situation. The ages had to be survived in this program. They have to survive long enough to not get wiped out, to develop a high level of fitness. And this gives what they're calling a typical run. So in a typical run, they're developing different levels of fitness, which is sort of like the ages having this like a darker blue, the non-ages having a lighter, but then they sort of like turn the whole thing into just green. So they're all represented by green, so you can compare it to better, but you can see where it was. So these two sort of like this two spots there, this like very dark green spot, this very dark green spot, they relate to these two where they have a high level of fitness. And
we can't see you pointing, Dr. Green, by the way.
Okay, so there's like the two, you can see those two have a high level of fitness and they represent down the green. So here is the sort of like non-ages and they're just represented by blue. And then they sort of like represent everybody in green. And you can see this big area, just sort of like the non-ages, that's sort of like a pale green. This kind of two areas, just sort of like the ages, they have a dark green. It shows they've evolved a higher level of fitness. So that's the thing that changes over time. They develop. The ages are sort of like able to develop more fitness, but their numbers can be like wiped out early. Okay, now let's go to the next sort of like slide. Okay, and this they're just showing like different variables. So they have all sorts of different variables they're calculating. D is, so like all these different graphs correspond to a different level of D, which is a different level of changing in the world. And then they have these sort of like 0.5, that's the different level of sort of like diffusion, how much they spread. And then they're having the number of sort of like, and it shows that what's happening after each amount of lifespans. So this is sort of like after sort of like just this amount of time. And this is, so this represents how often the ages win. Here you have, some of the times, this is like 100%, this is 0. In some variables, the ages never win. And in some variables, the ages can like win almost 100% of the time, depending upon the different variables. Okay, let's look at the next slide. So here's the next slide, and you can see the percentage of times the ages are winning. And you can see for certain variables, if you have the right variable, the right amount of diffusion here, which is 1, the right sort of like lifespan, which here is like 4, the right amount of sort of like change in the world, you could have situations where the ages win 100% of the time. But you could have other situations where the ages don't win at all. This is like, these are sort of like times when ages are not winning, depending upon the circumstances. The point of all this is whether the ages win or whether the non-ages win depends on the world they live in. Under certain circumstances, the ages, under all sorts of like variations, the ages sort of like drive the non-ages to extinction. But under other variables, the ages can be driven to extinction. In the real world, it means that an animal has to choose the right lifespan to fit the world they're living in. If they don't have the right lifespan to fit the world they're living in and to fit the circumstances of what's going on in the world, they can be driven to extinction. But if they have the right lifespan And you can see on this, it's only certain lifespans that they're winning on. If their lifespan got too short, it wasn't an advantage. It's already here. It was too short. They were different things, or sometimes too long. It had to be exactly the right thing. The animals have to evolve. This is sort of situations where nobody is sort of like the lifespan doesn't matter because nobody is really surviving past, it looks like. Here we have 20 lifespans. So nobody is surviving beyond, 20 number of generations. There's nobody surviving beyond 20 generations. It's sort of like it's not mattering. The point of all this is it's different. It's like how it applies to the real world. And it's showing in the real world whether it's good to be aging or good to be not aging totally depends on the nature of the world that you're living in. It depends on all these different variables. This shows.
Dr. Green, in what type of scenario would the non-agers survive? Is there any type of real world scenario that would take place? Is that what he's proposing?
A situation where non-agers do better, right? Is there a situation
right?
Better? Well, look at a fish. There are lots of fish that live 150 years, or fish that live 200 years, or turtles living 150 years, or an Arctic clam living 500 years. And human beings, like generally, a species chooses a particular pathway, and whether it turns out to be good or bad, that species does well or doesn't do well. But depending on the circumstances, non-agers, like reptiles, can do very well. And so there's lots of fish, negligible senescence, living 150 years. The longest fish lives like a Greenland shark. It's living like 400 years. This is an animal of negligible senescence. And it's doing very, very well. So you can see non-age.
So the variables for the fish, it seems like they would have, or the long-lived ones would have not very much change.
Well, there's other sort of things that shows how the different things fit into this. But basically, in other words, depending on the circumstances, aging or non-aging works out better. And another survey plan, they basically showed that if animals had an indefinite, like a universal distribution, like animals living in the ocean, there was never any benefit to aging. Those animals just could have a longer and longer lifespan. It was basically
definitely a benefit to not aging, you said. No, I mean, you said aging, but I think you meant not aging?
Non-aging.
Aging slowly.
Non-aging, the non-agers did very well if they lived in an environment with a universal distribution like the ocean. Like that living in the ocean promoted the idea of a very long life.
Okay.
The idea of a short life was living in an area where you're all living in the same area. That's sort of like, and then, but depending on the circumstances, animals would sort of like evolve different lifespans to meet their best needs. The point of understanding all this is the idea that aging or not aging isn't better all the time. In some situations, aging is better. In other situations, non-aging is better. That's why you have short-lived animals and long-lived animals, because the aging creates a very high price. It causes the death of a large number of animals, and it also has a benefit. So, depending on the circumstances of the world that you're living in, non-aging might be beneficial, having a very long life, or in a world that was changing very much, a short lifespan might turn to be better. However, so you can see, so the point is to understand that which is better was based on the nature of the world the animal is living in.
Mm-hmm.
These things changed very much depending upon what was going on. That's why animals have all sorts of different lifespans. As it was, but short lifespans have frequently been more successful. It's been in other words, evolution has for the most part gone in the direction of a short lifespan. And this way you can look in terms of insects. Insects are the most successful species in the world. The 80% of all species, 80% of all species are insects. It's sort of like numbers. They're like way more than anything else. It's sort of like mass. It's sort of like everyone agrees insects is the most successful species. Insects have a relatively short lifespan. Most of them live a year or less. A fly lives 28 days. On the other hand, insects can live for a long time if they feel like it. If you have a queen termite can live 30 years. A queen bee can live 7 or 8 years. So the animals can basically evolve pretty much whatever kind of lifespan turns out is better for them in a mathematical sense.
Mm-hmm.
So it's extremely specific to the circumstances. Each time you look at every single animal, and so to show you how specific it is for circumstances, you have the rock cod, all one species, and they can live from 13 years, the shortest living ones, to 250 years, the longest lived. So this is the exact same species. And depending on their sort of circumstances of what's going on with their particular lifestyle and how things are working out, they're having be having a 20-fold increase in lifespan, 13 years to 250 years, something like that. And it's the same species, rock cod. Shows it, and then they sort of found all sorts of different genes that were promoting to long-lived things, but all of them could have developed those same genes. It was just a case of what was better for that particular animal, depending on the particular environment. It was always sort of changing. All this gets fantastically complicated for each particular animal. But the general point is that the idea is that aging couldn't be beneficial is shown by this diagram. If aging was not adaptive, then all these sort of diagrams would be flat out zero. They'd all sort of go from 0%, 0%, no matter what they did, it was always 0% to ages 1 and 0% of the time, and the non-ages 1, 100% of the time. That's how these graphs would look if evolutionary theory was true. If aging was not adaptive under certain circumstances, that's what these graphs would look like. So this is sort of like showing that it's basically showing a huge level of complexity that depending on how they change the variables, they had different results. But the basic result is ages, the non-ages don't win 100% of the time. Sometimes they win, sometimes they don't. Sometimes the ages win, sometimes the non-ages win. And so it's completely different. And so you have two things and sort of like that's going in play. If you went back to the original slide, the very first slide, you can see what's going on is the evolution. You can see what's going on is the evolution of increased fitness. The ages of developing increased fitness, and it's the case of this sort of diagram, does the increased fitness compensate for the deaths due to aging? So the things that was like this sort of like explained, the next sort of question was, why is this? Why do the ages have a benefit over the non-ages? That's the sort of like question. Not just that they win, not just that evolutionary theory is completely wrong because aging is adaptive. Sometimes the ages win, but it's like, why do they win? What's their benefit? And the benefit is basically due to the fact that each particular generation can be better adapted to a changing environment than the previous generation. So each particular generation, and that's due to the effect of genes. Due to the effect of genes, each new generation could be better adapted because of new genes to the changing environment. If the genes caused bad mutations, those animals would die. But some of the genes cause good mutations, and those animals are better adapted. So now the question for evolving more fit species is, how do you introduce the animals with the beneficial genes into the breeding pool to make it take place faster? And the question is, the answer is, you do that by pruning the old animals. It's elimination of the old animals. That's the point of all the death pathways, to eliminate the animals that have lived too long. So now the question is, what's wrong with the old animals? Why do you want to kill the old animals? And the reason you want to kill the old animals is not that they're old. In other words, that was sort of like, circular thinking, that you wanted to kill the old animals because they had old and deteriorated. That's not the problem. The old animals are old and deteriorated intentionally. They didn't have to be old and deteriorated. That's senescence. They don't have to be senescence. The idea is that aging and senescence can be two totally different concepts. You can have a sort of like a 250-year-old fish, and it's sort of like not the slightest bit senescence. It hasn't decreased at all the number of offspring it's having. It's sort of like very, very non-senescent, very, very like fit. So the concept of aging and senescence don't go hand in hand. Aging and senescence goes hand in hand in humans. It goes hand in hand in mammals. So when we think of senescence and aging, we think of it as the same thing. It's much better to think of it as an older animal doesn't have to deteriorate. It could be maintained perfectly. The problem with the old animals is they don't have the new genes. You can understand this if you think in terms of a stealth bomber and a 30-year-old F-16 bomber. like a 30-year-old F-16 could be maintained in perfect shape. The 30-year-old plane is exactly the same shape and exactly the same level of fitness it had when it first rolled off the assembly line 30 years ago. So it's like old in terms of as a 30-year-old plane, but it's not senescence. It's not falling apart. It's absolutely 100% as good as a brand new plane because it's been maintained perfectly. And animals can do that. They can maintain themselves perfectly. But then, sir, I think, what's the difference between why would you want to replace F-16s? Well, you could want to replace F-15s if you had like stealth bombers. The stealth bombers, it's not that they're newer, it's that they have new technology. So it can't be seen. So that's what makes, in other words, it's the difference between the new planes have evolved a better sort of like technology than the old planes. It's not the old planes are senescent. It's not that they're sort of like senescent old. It's just the new planes have developed a better technology. And when you want to place the Air Force, you want to have more of these like new planes. So that's the idea of sort of like the animals. It's like they want to remove old animals that don't have the new genes into new animals that have the new genes that they want to sort of like promote. It's kind of like if you were thinking of it of a chess combination. Like I said, the point is it's a two-step sort of like idea. On one hand, you're having a sacrifice of like giving away material. But that's not, you're not giving away the material because that's a good thing. You're giving away to sort of change the situation because you got to get something better in return. So that's the idea of the aging thing. The aging is sort of like a hard price to pay. But the idea is that you get a bit, the return will be worthwhile. The return will be worthwhile because you have to evolve fast just to not go extinct. That's the sort of like the problem is extinction, not becoming extinct is frequently a matter of unless you evolve perfectly for your environment and you don't have to change, then if you may have to change to keep up with the competition. So that's the case of whether if you have to sort of like keep on changing to keep up with the competition, then it's better to have a short lifespan. But if you're completely well adapted to the world you live in, like say a crocodile, you don't need to have aging. You're perfectly fine with the way you are. And you're just like living a long time. So it's sort of like the term is sort of like it's different. The point of view is that mammals chose the pathway of senescence. And not understanding that results in a complete failure to understand what's going on. And if you take the position that aging can never be adaptive and you never have genes that promote aging, you're completely getting what's going on in aging in humans and terrestrial mammals absolutely backwards of what's happening. So that's the sort of like idea. It's just like there was a demonstration of how aging can be adaptive. And aging can be adaptive when you look at it through scientific models, not when you look at it. Doesn't seem like it's adaptive when you just look at it intuitively. If you look at it intuitively, you come up with the idea that, oh, we don't see anything good about it. When you come up with like something like this, a mathematical model, then you can see what's happening over 8,000 generations.
Mm-hmm.
It's sort of like, you can see in this study, these are all a huge number of variables. You can't sort of like figure that out in your head. It's like, okay, over like if we do this and this over the next sort of like 8,000 generations, it will have this effect and it'll make it beneficial because of this. You can't figure anything like that out without a computer program. You have to have all the variables that you sort of like in your plan and run it for 10,000 generations and see what happens. That's the idea. That the sort of like science is like, what's happening is something of extraordinary complexity. And the people who looked at it thought it was something of unbelievable simplicity. They thought it was the most simple thing in the whole world because they just left out sort of like, they made a model that has nothing to do with the real world. They completely left out the effect of genes. They completely left out the effect of sort of like change. They completely left out the idea that living things are totally different than inanimate objects because living things have the ability to adapt to change and change their level of fitness. A car can't do that. A car can't change its level of fitness, so it just wears out. So that was the idea. It's like a completely wrong idea of what was going on, just sort of like blocked understanding of aging for 150 years. Why? There's no reason why we should be like following an idea from 150 years ago that's not based on any scientific evidence, just because it's been around for 150 years.
I don't, maybe people don't understand what the value of the information is. And I think, that's why you've gotten so interested in this, is because you can see the writing on the wall. If there are genes that promote aging and death, then those genes, or there are things that we can target to change that, to slow it down, to delay it.
What you're saying is 100% true. And that before there was anti-aging medicine, and before there was the realization of pathways that you could sort of like block, there is no reason to know any of this. If there was nothing you could, prior to sort of like understanding how of identifying pro-aging pathways and having drugs that could block pro-aging pathways, none of this meant anything. It had no value. It didn't matter. It was just academic. It only becomes when you introduce the idea of anti-aging medicine resting on the whole idea of blocking pro-aging pathways, that it becomes something of extreme importance. So that's the idea, the way I see it. We didn't agree to a pro-aging pathways. We don't, so we're under no reason to why she shouldn't try to block it.
Yeah, and realistically, blocking these. So how long do you think we could live if we could find all these pro-aging pathways and block them? And what about,
the problem
we're
is
not getting disease, what about like skin aging and
they're like pro-aging pathways, you need pro-life pathways. You only you'd have to sort of like design them. Animals haven't designed pro-life pathways because they were never getting to there because they were dying of pro-aging pathways. So the pathways that sort of like to promote longevity don't exist either. Just sort of like because the major dominating pathways is the pro-aging pathways. But at least the point is, if you block pro-aging pathways, you sort of like block like the deterioration characteristic of middle age and age.
Yeah. Well, I'm all for that. Sounds great to me.
Yeah. Okay.
Okay.
So this is real complicated, but we can simplify it and so forth and so on. The critical point is that aging is adaptive in certain circumstances. It can be adaptive. So the idea that evolutionary theory that you can never select genes that promote aging is just a completely false idea.
Seems so.
It's funny because I'm no scholar, certainly, but, and I had no idea what classical evolutionary theory even was. I thought, I mean, this makes so much sense to me. This is just what, if you would have asked me if aging is adaptive, I would have thought, yes, it is. That's what survival of the fittest is. We age, therefore it must be adaptive. But, you know, I don't know.
Yeah, it's not a mistake of biology.
That's the
All right. Well, can we wrap this up? Dr. Green, is there anything else? Closing?
I have nothing else to say aside from the scientific evidence shows that the idea that aging is not adaptive is a completely wrong idea.
All righty.
Sounds great. Okay, well.
All right, Raptors. Until
Okay.
next time.
Till next time.